This is Module 1, Lecture 1.2. This is the second part of the human movement lecture, looking particularly at biomechanics. So in the first lecture, we went through human movement and described the joint actions, the actions that occur in the sagittal, frontal, and transverse plane, introduced some directional term, but basically looked at the human body from this three-dimensional coordinate. We also shared that human movement is described based on the plane, so transverse, sagittal, or frontal plane. The direction, so forward or back, up and down, side to side, relative terms like medial, lateral, anterior, posterior. And then we had special names for those joint actions. For instance, movement that was moving anteriorly in the sagittal plane was called flexion. Movement that was moving laterally in the frontal plane was called abduction. The one other concept that we started to introduce, we were talking about the types of motion that exist in physics. So just looking at physics outside the human body, movement is usually categorized into four basic types: translatory, rotary, curvilinear, and general. General being some combination of all the three previous ones. Translational or curvilinear are more linear motions, moving straight, whereas translation is moving purely straight, whereas curvilinear is going over a curved path. And then rotation is that wheel example or a door hinge where you have an axis of rotation and then segments moving. And what was shared was that all the major joints of the human body, all movement is rotary motion or some kind of rotation where you have a fixed axis, and you can see these arrows demonstrating or delineating the rotation that's occurring. So we said that motion is described in terms of the quantity of degrees of rotation. So 360 degrees in a circle, 180 degrees, half of that, 90 degrees, half of that. Now, it doesn't mean that movement can't result in a linear fashion. So this example here on the right shows the hand reaching linearly, going straight across, not rotationally, to reach for that glass. Although the output is a linear movement, the production of that is rotation, but instead of just happening at one joint, it's happening at multiple joints, there, and there. So what we're going to talk in this lecture is the whole aspect of this rotational motion. We'll talk about some of the forces that are producing that internally, and then taking consideration of the forces that are happening externally for that. So here's just some more text that talks about, and you have the slide in your notes, that the linear motion is looking more at a particular distance, whereas rotational motion is looking at that axis of rotation. And these axes were described in the first lecture. We talked about these imaginary pivot points that were moving perpendicular to the planes. So in this case, this example here, you see this transverse plane. This is that longitudinal axis, the axis that's moving superior inferiorly, 90 degrees to that plane. And so all motion that's occurring in this transverse plane, which is left or right rotation or horizontal ab and abduction, is occurring in this transverse plane with this as the axis of rotation. So then we started to ask what causes these motions. So we're describing these movements in these planes. We're talking about the joint actions. We're talking about what the joints are doing. But what about the forces that are actually causing this to occur? And the human movement, the skeletal system cannot move unless there is some force acting on it. That force can be external, or as we were talking, the force can be internal, which is being generated from the muscular system. So from just a straight up physics perspective, the definition of a force from a physics or engineering perspective is any push or pull. So push or pull exerted by one object on another. With the human body, we're either going to deal with external forces coming from typically gravity, or with the internal forces, we're dealing with muscle contractions. We get into this terminology of motive versus resistive. Motive forces, think in terms of motive, and it relates to the word motor. These are the things that produce force. So when your car is just a static object, it can't go unless the motor is driving the forces, and those motors are internal. And then the resistive forces are the forces of friction or air resistance, or in our case, gravity. So we'll talk about these two different types of forces. So as I said, the internal forces are these muscular forces. So these are the muscles being generated by the body. And it's these muscular forces here. We defined earlier that a force is nothing but a push or a pull. In the human body, think of the muscles as rubber bands. They can generate lots of tension. They can pull in towards each other, but they can only pull, they can't push the two ends together. So all of the muscles in the body are designed in a way where this is a muscle that's been separated out. Let me just get this box out of the way. And you see the muscle belly here. You see the muscle, and then it continues on, and it becomes continuous with the tendon, and the tendon becomes continuous with the periosteum, the covering of the bone. And so this is one aspect, and this is reproduced on the other end. Same thing. So a muscle attaches from one bone to another bone, and so you can see the example here. Here's the innominate, the part of the pelvis here, and then there's the head of the femur, and this is the glute medius muscle. And it doesn't matter, we just picked an arbitrary muscle. And you can see that these arrows represent the lines of force. So when the muscle actually gets the input from the nervous system to do its job, which is the only job it can do is generate tension, it's going to pull this end and this end as close to each other as possible. Now, which end moves is really dependent upon the other muscles or the positioning or orientation of the body, but the muscle doesn't know that. It's just trying to pull this end towards this end as best as it can. So that's the internal forces, and that's what leads to the movement of the body. So these types of muscle contraction, this types of muscle interaction is called a muscle contraction. And the muscle contraction is this attempt to pull both ends together. So when I say attempt, and that's kind of important that we talk about this attempt, is that not all muscle contractions result in this end moving closer to this end. It's an attempt. They try to pull both ends, but doesn't necessarily happen based on the environment. So the types of muscle contractions that exist are three. You have what we just defined there, where the muscle actually gets the input from the nervous system. It tries to contract, and the muscle tension overcomes the resistance, and both ends are able to come closer together. So in this image here, it's showing a leg press going from a bottom position up to lockout, overcoming gravity. In an eccentric contraction, you're getting muscle tension being generated, but instead of a shortening result, you're getting a lengthening result. So I'll back up one slide. This muscle is trying to pull both ends together, but the tension is less than the resistance. So in this case, the weight plate is greater than the resistance is greater than the muscle tension, and so the resistance wins and pushes down, but the weight plate's not moving as fast as it could, so there is some force being generated by the muscle. It's just not as great as the concentric contraction, which is overcoming that resistance. So you have all three images here are the muscles trying to contract. This one results in the muscle shortening. This one results in the muscle lengthening. And then iso means the same. Isometric contraction means that there's no change, that the amount of force being generated is exactly equal to the amount that gravity is pulling down on it, thus no movement is occurring. So these are the muscle contractions that we're going to talk about in length in another, I guess I intended that pun, in length, that we'll talk about muscles in more detail in our third lecture when we get into muscle contractions, and this will take quite a bit of time. We've already kind of talked about this in class. If not, we will be talking about it in class, and we're just introducing these concepts. But you basically have your three types of contraction: concentric, eccentric, isometric. And you can look at it. The easy way to look at it is looking at it from is it shortening or is it lengthening? That doesn't always tell you the picture. The other criteria that needs to be met for muscle contraction is that there needs to be an attempt at contracting, the attempt at generating muscle tension. So just because a muscle is shortening or muscle lengthening doesn't necessarily mean the muscle is contracting. So there's got to be a response to the muscle tissue trying to contract, the attempt to contract or shorten, and then the result of that. If it's shortening, then it's defined as a concentric contraction. If it's lengthening, eccentric contraction, or if there's no change at all, it's isometric. The best way really to look at muscle, which is more difficult, but in the long run makes things easier to see, is this whole concept of the muscle resulting movement in response to gravity. So when you're looking at muscle contraction, you're typically looking at joint motion. So you're looking at some output of movement. So is that person running, jumping, throwing, pressing, pushing, sitting up, whatever the activity is. And so we're looking at the joint response or the joint output. And if that joint is overcoming gravity, then that is acceleration, right? It's accelerating because gravity's trying to pull it down. And so you're generating muscle force, you're overcoming gravity. That's always a concentric contraction, always. If you're going with gravity, succumbing to gravity, and you're moving slower than gravity, then you are decelerating. So anytime you're moving faster than gravity or overcoming gravity, that is a concentric muscle contraction. And then anytime you're going with gravity, gravity's pulling down, your joint response is the same. It's going in the same direction, but it's moving slower. If you're driving on the expressway and you're going 60 miles per hour and someone to the right of you is starting to go 55 miles per hour, they're slowing down. They're going in the same direction, but they're moving more slowly. They're putting the brakes on. They're decelerating. Okay. And then isometric is the obvious. There's no change, a static position. So in order for this to occur, human motion, these muscles that we're talking about have particular terminology or different titles, and these titles change. But basically, the agonist is the muscle that produces that acceleration or deceleration. It's the muscle that's actually doing the work. The antagonistic muscle is the muscle that's not doing the work. So this is why we made it clear, let me back up one slide, of why the whole shortening and lengthening can be misleading, is that in this relationship with agonist and antagonist, since muscles only pull and they can't push, all muscles are paired in a way where one muscle can pull and move a bone into a particular position, and you have another muscle on the other side that's able to pull and move you back into position. So if you look at your biceps and triceps, when you bend your elbow, the biceps are working as the agonist. They're contracting. They're the ones doing the work. So that's a concentric contraction. The antagonist muscle, the triceps, they have to relax. They are lengthening. And this is where the confusion is that lengthening doesn't necessarily mean an eccentric contraction. It just means that the muscle is lengthening. The fact that it's relaxing is your evidence right there that it's not contracting. So that's why sometimes the lengthening and shortening can be confusing because it's not always appropriate. But is it overcoming gravity, going with gravity, getting the signal to contract? That's the better aspect. And then the synergist and co-contraction are just looking at stabilizing function. Like I said, we'll go into more detail here. I just added this slide to justify why I was saying that it's better to look at it from acceleration versus deceleration. All right, so these are the internal forces coming from the muscles. Now we're going to start talking about the external forces, and the external force that we mostly deal with, that everyone deals with every single day, but what we deal with from an exercise or resistance aspect is this gravity, the force of gravity, which is always pulling down. So every exercise you're trying to do, whether it's body weight, free weights, machines, outside of elastics like tension tubing or inertia or resistance bands types of components, is always you trying to overcome gravity, trying to pull something down towards the ground. You're lifting something off the ground up into the air, and that's what's causing the tissue overload. As I've said or shared, or as you experience every day, gravity always pulls down toward the earth. There is never a situation where gravity is pulling in another direction, and the gravity is always present unless you are in outer space. The one neat thing about gravity is that it pulls at the same time at all objects. So a feather without air resistance will fall just as fast as a bowling ball, no matter what height you drop it at. Okay, why a feather typically doesn't hit the ground first is because the air resistance has more surface area, and it's lighter, so it's more susceptible to the wind and the air versus the bowling ball. Now, although gravity is always pulling down, it doesn't mean that the line of force is always down. What that means is if you're doing a cable pull down or cable row, you have a pulley situation where the cable is taking on the load of the resistance, but the resistance is still coming from gravity trying to pull that down. So you can see here that gravity is illustrated in this pink arrow here. So you got 100 pounds that is pulling down. And when I grab this cable and I pull it, although the force is pulling my arm up, so I have to pull down, I'm still, when I pull down, the result of this movement is that weight goes up, so I'm overcoming gravity. So just be aware that machines that have an axis or a lever, like fixed plate type machines with a selector plate, or pulley stacks, high and low pulleys, they're still under the effects of gravity. The weight, the resistance is still under the effect of gravity. It's just that the cables redirect and redistribute forces. So how do we interact with these internal forces versus external forces? So I've talked quite a bit about these planes of motion and the axis of rotation. And if it hasn't been clear yet, zoom in here. If it's not clear yet, is that movement is all about rotation. And so like here on the frontal plane, you can see this abduction and adduction of the arm. That red dot right there represents the pin, the axes that would be going through and having that rotation. This arm is rotating about that pin right there. If I look on the sagittal plane, this elbow is rotating, this lower arm here is rotating about that pin right there. And so you have these these relationships between internal and external forces being experienced through the body via the skeletal system. So the bones take on most of the load. The movement occurs at these joints where these axis of rotation is at, and that movement is rotation. And how that rotation occurs has to deal with the balance of forces across the body. Let me get back to here. So what we're looking at here in terms of our gross movement is really represented here on an isolated basis. So there's your lever, your bones, there's your axis of rotation, there's your muscle force, and then in this case we have a weighted ball, or it could have just been the weight of the arm as our resistance force. And so since we're dealing with axes of rotations and muscles and forces being applied at different points, we're really getting into this new concept of looking at lever systems within the body. So a lever, from a mechanical aspect, has four parts. There's a lever arm, there's the actual pivot point, or sometimes called the axis or fulcrum. You have the effort, and then you have the load, or sometimes called the resistance. So those are the four components that make up a lever in any kind of mechanical or machine or engineering environment. In relation to the bodies, the bones act as the lever arms. So these are the forces. The forces are being transmitted at certain points through the bones. The axes or the pivots or the axis of rotation is the joint itself, so where these two bones come together. The effort, the force that's producing the motive forces to move the loads or move, period, is coming from the muscles exclusively. And then the load, the resistance, is often gravity, sometimes other resistance like elastic, air resistance, or water resistance, but basically it's coming from the environment. So these four things interact together to produce certain relationships for us to actually move. Levers are classified. Well, most of us are familiar with levers. I actually don't even know if this is on playgrounds anymore, but when I was growing up, we had teeter totters. I'm sure they're still around, but someone probably got upset because they weren't safe, and I don't know. But anyhow, we know this principle of leverage by looking at that we have this pivot point, this fulcrum, and someone sits on one end and another person sits on the other end, and based on how big someone is or how little someone is, you can adjust the lever or the leverage by changing your distance if you move further out or further in. And that's basically what we think of as levers. Those components are absolutely true for a lever system, and this is actually defined as a first-class lever, which we'll talk about in a couple slides. But the body is set up in a similar way. It has the components, just arranged slightly differently. So instead of the pivot being between the load and the effort, the pivot, the joint, is on the far side of both the effort and the load. The effort is actually, the muscle force is actually at a disadvantage. It's closer to the joint, and the load is far away. So this is called a third-class lever, but this slide is just representing the relationship that we kind of know what teeter-totters and balance levers look like. The same concept is applied into the human body. So levers are used to really magnify or not accelerate, but expand the capacity of the human body. We're able to take a little bit of energy, and exponentially turn that into forces that we can sometimes can't even conceive of producing on our own. I know I've used the example, if I haven't used it yet in this class, I use it. It's my favorite example, that you guys have all heard the sound of a whip before, that cracking of that whip. Well, that sound is the tip of that whip breaking the sound barrier, which is 360 miles per hour. And that all comes from the human wrist moving in the sagittal plane. Okay, and so that little bit of movement, which the human body cannot produce on its own, is able to compound and magnify and create into that component. If you think about what the human body can do, like in terms of the amount of times our body weight we're able to move, like how much load, when you think of like 200-pound individuals, athletes that are lifting 1,000 pounds, 5 times their body weight, someone able to throw a baseball 100 miles per hour. And I'm using extreme examples, but let's just look at basic examples of someone being able to squat 200 pounds or someone throw a baseball at 60 miles per hour. These are huge amount of forces that are able to produce that are coming from small amounts of muscle tissue right? So it's kind of neat how the body's able to use these forces internally, externally to produce these great movements. It's all based on this leverage capacity. Um, these leverage systems are able to take that, again, that small amount of force that the muscles produce and use that to produce a component into a larger output. This whole relationship of smaller and larger, or smaller and in most of the case of the human body faster, is called mechanical advantage. So mechanical advantage based on these levers will either give you a force advantage or a speed advantage. So in the learning process too, what's unfortunate is we usually think of leverage in mechanics of we're using a wheelbarrow to lift up a load, or we're using a pry bar to lift something up, we're pushing on the farther ascent of the door. We're always think of levers in terms of force levers for us in terms of making things easier. Unfortunately, the human body isn't designed to really use force levers. Where the body is usually designed is to get these speed advantage, speed levers. Just the aspect is that they can't coexist. A leverage system is either set up to produce force or to produce speed, and most of the joints of the human body are meant to produce speed, where most of the forces we think about in nature, or when we think of mechanics or engineering and construction, are meant to modify force. So let's go through these levers. There's only three, and these are the classes of levers, and they're basically identified by how the three primary elements are arranged. Now remember I said that there's four elements that make up a leverage system. You have the effort, axis, and load. The axis is also the fulcrum or the pivot. The thing that's always present, no matter which lever system, is the actual lever itself, in this case the bone. So you need to have a lever in order to have a lever system. What delineates between the lever systems now is the relationship here. So a first class lever is the first one I introduced to you guys, which is the teeter-totter, the balance beam. This has a lever that is the load and the resistance are equally split between, not equally split, but you have a load on one side and the effort on the other side. The second and third class lever, they're set up in a way where the axis of rotation, or the fulcrum, is on one side, and both the lever, the effort, and the resistance force is on the same side. What differentiates is who's further away. In the second class lever, it's the effort. So I just went through the words here, and it can be ultra confusing, so I'm going to show one picture, and it's going to make all types of sense, so at least better sense. So here's your first class lever. Here's your pivot point, your effort, and your load. So you have your one kid on the one side of the balance beam, the one kid on the other side, and based on how they move or what kind of force they produce, they're equally balancing one another. And you can appreciate that if one kid weighed 60 pounds, another kid weighed 60 pounds, and they didn't move, nothing's moving here. Now the second and third class lever, you'll see that they're set up exactly the same. The pivot is not split between the two like we think of in terms of our playground equipment. You have your pivot, and then the beam here represents the bone of the lever, and then you can see here that it's either the efforts on the far end or the loads on the far end, and depending upon which one, like I had said earlier, typically we think of, we can do a little bit of effort here and we're able to move a really heavy load. So I can put 600 pounds on a wheelbarrow here, and when I lift this up over here, I can move it and lift it. There probably wouldn't be any way that that person would lift up 600 pounds on their own, or at least do it as many times as they could if they didn't have this mechanical advantage. Okay, that's not typically how the human body is set up. The human body is really set up here as a third class lever. So instead of me lifting way out here with the load here, I'm actually at a force disadvantage, because here's where my muscle is pulling and I'm trying to lift a load way over here. Okay, so you can appreciate, like if you try to open up a door and you push closer to the hinge end instead of by the handle end, how much effort you actually have to put forth. And people think that's at a disadvantage, but remember, you might be at a force disadvantage, but you're at a speed disadvantage. I'll demonstrate this in class. We'll have a discussion about it, but basically think of this. If I lift this end right here 1 inch, the amount of energy it takes me, or the amount of time it takes me to move 1 inch, this here didn't move 1 inch. This moved exponentially. It's rotating. So 1 inch of movement here is actually creating 6 inches of movement over here. So the amount of time it takes me to move 1 inch, I'm basically teleporting or slingshotting. What's the word? Slingshooting myself. Again, for every 1 inch movement, I'm accelerating way at this end here. So I only need to make small little changes here through muscle regulation to get huge changes over here. And you can look at the inverse over here. In order for me to lift this 1 inch, I have to lift this 6 or 7 inches to get that to lift up 1 inch. So although you're at a forced disadvantage here you're at a speed advantage, and that's just the inverse between those. The next slide here kind of shows some examples. Same thing, here's your fulcrum load effort. This is what it would be like in the mechanical environment, and this is where it exists in the human body. So here's your first class lever, your balance lever. There's only one or two places that it exists really in the human body. Your second degree lever, your force lever, and then where the majority of that your leverage system is here, where you have more precision and speed production versus force production. All right, and so the last thing that this unit comes into that's quite important is we identify the forces that are existing in the body, right? The internal forces from the muscle and the external forces from the load, the dumbbell you're holding in your hand. But when we start looking at human movement or modification of exercise or movement output, we're not dealing with forces alone. We're actually dealing with this concept called torques. And since we're dealing with the leverage system, we talk about the forces, the internal muscle forces, or the 25-pound dumbbell that you might be holding, or the 15-pound dumbbell hold. But the dumbbell in your hand or the muscle tension itself is not what we're really dealing with. What we're dealing with are really torques. And so the primary difference between forces and torques is that a force is a push or a pull, in this case a pull, but a torque is a force that has some distance to it. All right, and that distance is the mechanical advantage that's being calculated. So a torque is a force that results in rotation, where the force itself is just a linear component. So it's a straight component, either straight up or straight down. But since it's acting on a lever, a torque, at some distance away from that axis of rotation, those numbers aren't quite the same. So a 25-pound dumbbell, based on where it's applied, what kind of distance it has, is going to have a different effect, a different response in the body. So like I said, we will go through this in quite detail in class with quite a bit of examples. I do want to leave you with this one thought process, because it's very much this whole concept of torque manipulation is used quite often in the fitness industry to overload tissues in particular ways. And so I'll just leave you with this. You have this should be the same people, but I couldn't find two images or the same. But anyhow, you have an individual, and just assume that these dumbbells are the same. So I said 15 pounds. Just think about how long this person can hold 15 pounds up over their head, and think about how long this person can hold 15 pounds out to the side. The dumbbells are exactly the same. The distance of the arm is exactly the same. Obviously, this would be a lot easier to do, or he'd be able to do this a lot longer than this person here. Even if you didn't have a 15-pound dumbbell, if you just had your arms up to the side, I would bet that this person can hold 15 pounds up over their head longer than this person can hold their arms up to their side. But we'll just think about that, and we're going to discuss that in class in more detail. Okay, so like I said, we'll talk about torques later. Just a couple other concepts that are quite related to biomechanics, but may not, they don't fit in their own lecture here itself. But this concept of open chain and closed chain comes up quite often in exercise selection. These are terms that are engineering terms that are borrowed by movement scientists and particularly used in physical therapy. When we use them, the definition in an engineering sense doesn't quite transfer over into a movement sense, but basically the way it's used in the fitness industry or kinesiology, the movement science component, is that closed chain activities are activities where the distal end is not free to move, so it's either fixed to the ground or fixed to some machine. And open chain is that the distal end is free to move. That's basically the concepts. The engineering term for closed chain and open chain is that any movement at one joint in the system leads to predictable movement in the other joints, whereas the open chain is unpredictable movement. There's randomness there. But basically here, like a push-up would be a definition of arm movement that is closed chain, but that dumbbell that is open chain because you don't know how that's going to turn out. And you can have 8 people do an elbow flexion. Unless the arm's attached to the ground, it's going to move around. And so the way this works is in terms of a therapy aspect, that these tend to be less stable or more stable. So people can argue one way or the other. They're actually poor terms to describe exercise, but they're used nonetheless. So if someone looks at like closed chain activity versus open chain activity, closed chain activities you're going to think of as more your body weight type components like squats and push-ups and so forth. And then open chain are going to be your free movement type aspects. So like if you're kicking a soccer ball, the foot that's planted to the ground is closed chain, and the foot that's actually kicking the ball is open chain. So just think of that concept as, is the foot or the hand free to move? Is it fixed because it's stuck to some surface or some machine? It's closed chain. If it's free to move, then it's open chain. These next two slides get into this whole aspect of balance and alignment in the body. We'll talk about alignment quite a bit in KIN 231 fitness assessment when we look at postural assessments. But in this aspect of alignment of the body, it's talking about this concept of center of gravity. And this is the theoretical balance point of the human body. So if you took all the mass of the body and found one spot that you can balance on someone's finger or a pivot, and you'd be equally balanced, that would be the center of gravity. That's typically right here just above the pelvis at the level of the navel, but of course it's going to differ for each person based on shape and size and distribution of body mass. This image here shows that that center of gravity doesn't have to stay within the body, that it can be at this theoretical point outside of it. And why this becomes important is it gets into this whole concept of balance and base of support. So the center of gravity is this concentrated center of mass where things would be equally distributed. Base of support is this concept of how much space your contact to the ground is taking up. So you can see different alignments here set up with different foot placements. So here's someone's footprints here. These are footprints with fingerprints like a 3-point stance or a 4-point stance in football. And basically it goes as this. Balance is defined as the ability to keep your center of gravity within your base of support. And so if you're looking down from someone's top of your head and you're looking down onto the ground here and you see this theoretical area that your body's picking up, your base of support is coming through your body straight down to the ground here. So that center of gravity is still within the toes. As he's moving forward, bending forward, when he's standing up here, center of gravity is right through from here, straight down to his knee, right in the middle of his foot. As he starts to bend forward, that center of gravity goes further and further and further. So in this situation here, here's where the base of support would start, and then it moves. And at any point, that center of gravity moves within the base of support, he's going to be able to control his environment. If, for whatever reason, that center of gravity moves outside of that base of support, now you lose your balance and something has to change. Either that base of support has to move to capture that center of gravity, or the center of gravity has to move back into the balance of support. And typically what would happen is he starts to bend forward, bend forward, bend forward. You start to get off balance. What does someone do? They usually take a step forward, and now that center of gravity is within the base of support. So this is just looking at stability versus balance and what it takes in order to keep someone upright. Where this comes into play typically is when you look at exercise challenge. So what's happened in our industry right now is there's this huge plethora of like functional training and trying to make things more complicated. So let's take a bicep curl, which by itself is just a single joint exercise, but let's do it in a situation where we're in an unbalanced perspective, either standing on one leg or on a stability ball or on a foam Airex pad, or some crazy circus type trick where you're standing on a balance ball blindfolded with some vibrational plate going on, right? So you can make it as challenging as you want. And basically, the more challenging your base, the more challenging the environment is, the more difficult it is for that exercise. You can either use that for progression to challenge your clients, or you can use it for regression to teach your clients. So if you have clients that are very deconditioned, that aren't very, have good control of their lumbopelvic aspect of their spine, or they have some injury or something going on, that maybe a standing position might not be the best way to do an exercise, and maybe a seated position where you have your 2 feet down and where your butt's making contact with the ground, now your base of support becomes much larger, become an easier way to learn that exercise. And you want to learn before you progress. And so sometimes just basic standing, sitting even, so sometimes maybe laying down might be the best aspect. So it's just ways of looking at the relationship between base of support and the stability of the environment. And the more stable someone is, the less resources they have to commit to balancing just to perform the exercise. And so they can take all their resources and put that all towards the exercise itself. As they become more competent with the exercise, it becomes more second nature. Then you want to make it more challenging, and you can challenge those resources by distracting them, by making them stabilize while they're producing the activity. So that really gets into why we're doing functional training, and you should really be diligent about making sure that the exercise you have your clients do are purposeful and that you understand the risk and benefit. Just having someone do some crazy balance exercise just to do it without really understanding the contextual relationship is a disservice to your client. So that's it for the physics. This terminology here just describes what I was saying about keeping that line of gravity from the center of gravity, center of mass, contained within that area of the base of support. And as long as that theoretical line coming down from that center of mass is within this boundary here that's set by your contact to the ground, you'll stay stabilized. Okay, so that's it for the biomechanics component. This really gets into a lot of concepts of the big thing that we're going to talk about in classes is leverage system. But really, when we start looking at torques and how we can manipulate forces to produce different outputs, and it's the basis of this question here, which we'll talk in class. So hopefully that was helpful, and stay tuned for our next lectures.